Antiderivatives and indefinite integration. In this section and chapter, we introduce a different concept in comparative to the derivative, where the derivative was concerned with the tangent slope of a function. Here, the so-called antiderivative is concerned with the area as that functional particle would move throughout its course. Is it possible to calculate the area mass of which it leaves or it spells out? We call the integration or the antiderivative the area under the curve. The curve is generated by some type of vector or particle as it moves along through space. The so-called area by which the particle moves through and leaves behind, is it possible to calculate that particular area? Well, here we give the introduction and we call it the antiderivative. The antiderivative, or the indefinite integral, is said to be no more than the inverse of the derivative itself. So when you take the derivative of a function, that which remains, or the result of that, is said to be an antiderivative. Let here function capital F with its derivative little f of x is equal to 3x squared. We'll say that capital F is the antiderivative, x to the third, because the derivative of this capital F of x is equal to 3x squared. So you compare x to the third with 3x squared, and so they are the inverses of each other in terms of the so-called antiderivative versus the derivative. The definition of antiderivative of function capital F is an antiderivative of f on some open interval I, where capital the derivative of capital F of x is equal to f of x for all x and I. So we give the notation that capital F is said to be the antiderivative. Later on, we will claim it to be the integral of little f. Here, the representation of antiderivatives is such that capital F is the antiderivative of little f on some open interval I, then g is the antiderivative of f on the interval capital I, if and only if g is of the form g of x is equal to f of x plus some constant. And the constant c is always not created but exists because if there was something that was measured before, and by a derivative of a constant, the derivative of a constant is 0, then what was left, if you're looking at the antiderivative, well, there has to remain a constant as well. So we don't necessarily talk about the integral or the antiderivative of 0, but we understand that that it is something that inhibits or exhibits some type of number that we call a constant c, of which to be determined. Basic integration rules. I think the key to remember from the basic integration rules is the derivative of x to the n. Where you would say that this is n times x to the n minus 1. And what corresponds to it is its power rule for integration. The integral of x to the n dx is x to the n plus 1 divided by n plus 1. But here, n cannot equal to negative 1. We have a different definition for that. So you see the basic differential or differentiation rules for taking the derivative of certain functions. Coupled with it would be its antiderivative or integration. So the integral takes the result of the derivative and it gives you back again the original function if you look at the two as being inverses of each other. Likewise, with the trigonometric functions, we have derivatives of such, and we can also take the integrals and get very similar results, just in the inverted form. I think outside of the trigonometric functions, the key integration rule is the power rule. I think you'll see this one a lot. In this section, we introduce differential equations very in a simple way. Differential equation is any equation that contains a derivative or a differential. And back in chapter 3, section 9, we dealt with differentials, so you're familiar with dx and dy. Let's look at some problems. And so for this one, we integrate the x. This is x to the first power, understood to be. And so this is x, use the power rule, to the second power divided by 2, plus this is the integral of 7, which becomes 7 times x. Why is that? Because there is understood to be an x to the 0 associated with that 7. So we integrate this. This is 7. We can put the constant in front of the integral, times x to the 0 dx. So this is 7 times x to the 0 plus 1 is 1 divided by 1 plus some constant. So we get 7x plus c. So here, we have 1/2 times x squared plus 7x plus c. We come here, and must I say that you can break up the integrals into its parts, because the integration is said to be a linear algebra. So this is 1/6 times x to the 6th plus the integral of 1 dx is x plus a constant c. We integrate here. You integrate the x to the 3/2 plus 2 times the integral of x dx plus the integral of dx. So this gives us x to the 3/2 plus 1 is 5/2 all over 5/2 plus 2x to the second divided by 2. This is x to the first. 1 plus 1 is 2. X to the second divided by 2 plus x plus a constant. Now we can clean that up and write this as 2/5 times x to the 5/2 plus x squared plus x plus the constant c. This is the integral of x to the 2/3 dx. This is x to the 2/3 plus 1 is 5/3 divided by 5/3 plus a constant. And you can write this as 3/5 times x to the 5/3 plus c. Come here, you can write this as the integral of x to the -5 dx. Again, we use the power rule. So x to the -5 plus 1 is -4 divided by -4 plus a constant. And we can clean that up and write that as -1/4. Let's write it better. This is negative. This x to the -4 goes downstairs too, so it's -1 all over 4 times x to the 4 plus c. We break this one up into 2 parts. This is the integral of, this is x over the square root of x plus 6 over the square root of x dx. Now we understand that this is x times x to the negative 1/2 plus 6 times x to the negative 1/2. We want to try to write the terms with respect to the power rule, right? The power rule we use that comes in convenient for us. The integral of x to the n dx is x to the n plus 1 over n plus 1 plus c here, where n is not equal to negative 1. So this is one of our favorite techniques if it's applicable. Right? So this is the integral of x. This is to the 1/2, simplifying, plus 6 times x to the negative 1/2 dx. So now we can integrate. We do not hesitate. So this is x to the 1/2 plus 1 is x to the 3/2 power divided by 3/2 plus 6 times x to the negative 1/2 plus 1 is to raise to the 1/2 divided by the 1/2 plus the constant. And we can write our answer. This is 2/3 times x to the 3/2. This is plus 12 times the square root of x plus c. And for this one, we FOIL, so we have 3x squared minus 2x plus 3x is plus x minus 2 dx. So now we integrate. So this is 3x to the 3rd over 3. That's it. Plus x to the 2nd over 2 minus 2x plus a constant. And you can just write that as x to the 3rd plus x squared over 2 minus 2x plus c. Okay. Now, in terms of if you're integrating with respect to the trig forms, let's see. So this is 5 times the integral of cosine x dx plus 4 times the integral of sine x dx. You integrate the cosine here, and that gives us sine. So this is 5 times sine x. You integrate the sine, you get negative cosine because the derivative of cosine is negative sine. So this is negative 4 times cosine x plus some constant. So you can write this as the integral of dt minus the integral of cosecant t, cotangent t, dt. Now, for the cosecant cotangent, it might be helpful to just recall the derivative of cosecant x plus the negative cotangent x cosecant x. So if you flip that and take the integral, watch this, the integral of both sides, I guess it's better to write it like this. This is negative cotangent x cosecant x is equal to the derivative of this cosecant x. If you integrate both sides, the integral of the derivative gives us the identity term there. So, and I'm going to put this negative on the opposite side over there. So we have the integral of cotan x cosecant x dx is equal to negative cosecant x, and then plus some constant. So So my point is, no need to memorize the integrals of the trigonometric functions. Just memorize, like you already have, the derivatives of the trigonometric functions, and just in the reverse. And so the derivative of a term that you get a negative result for the trig is that result. Integrating that term, you get the negative back. So here, the integral of dt is t. The integral of secant cosecant t cotangent t dt is going to give us negative cosecant, negative times this negative is positive cosecant t plus some constant. So here, well, the derivative of tangent is secant square, so this is tangent theta. And the integral of sine is negative cosine, so this is plus cosine theta plus theta. Now, tangent square y plus 1 is equal to directly secant square. So this is the integral of secant square y dy. Now, if the derivative of tangent is secant square, so then the integral of secant square is tangent. So this is tangent y plus some constant. Right? So do you see that? Cosine square theta plus sine square theta is equal to 1. Dividing through by a cosine, we have 1 plus tangent square is equal to 1 divided by cosine, which is secant square theta. Right? And we know that the derivative of tan x is equal to secant square x. So then the integral of secant square x dx is this term here, tangent. Now, in terms of a particular solution that satisfies the so-called differential equation, a differential equation is any equation with a derivative or differential in it. So this equation here has a derivative in it. So what I want you to understand is that when you take the integral of a derivative, you get the original term. So here, h of t will be the integral of h prime of t, because the integral is the inverse of the derivative, right? So this is the integral of, well, h prime is this 8t to the third plus 5 dt. You integrate this. This is 8t to the fourth divided by 4 plus 5t plus some constant. So h of t is equal to 2t to the 4 plus 5t plus c. They give us initial condition that h of 1 is equal to 2 times 1 to the 4th plus 5 times 1 plus c. That's equal to negative 4. So we get 2 plus 5 minus 4 implies that c is equal to negative 4 minus 7. So we get negative 11. So we conclude that h of t is equal to 2t to the 4th, right, plus 5t, and then plus c, which is minus 11. Now, it doesn't matter how they expand it. The first derivative, if we have f of x is the position f prime of x, gives us the velocity f double prime of x gives us the acceleration. So here, f prime of x, can you see the prime, is equal to the integral of f double prime of x dx. F double prime is given to be the integral of x squared dx. So this is x to the third over 3 plus some constant. Now f prime, the initial condition, f prime of 0 is equal to 8. So f prime of 0 is equal to 0 plus c. That's equal to 8. That implies that c is equal to 8. So this function here for f prime of x, that becomes f prime of x is equal to x to the third over 3 plus 8. So now f of x is its integral, the integral of f prime of x dx. So we integrate x to the 3 plus 8 dx. So f of x is equal to x to the 4th divided by 3 times 4. We get 12 plus 8x plus c. Now f of x has an initial condition as well. F of 0 is equal to 4. So f of 0 is equal to 0 plus c. That's equal to 4. This implies that c is equal to 4. So we conclude that the original function f of x is x to the 4th over 12 plus 8x plus 4. That'll do it.